Very good. Let's hope I have enough charge. Yes. So welcome back, and we are going to pick it up from where we left it last time. So last time we, during last few lectures, we introduced stochastic dynamics, Langevin processes and Langevin dynamics, path integral, representation of the conditional probabilities in Langevin dynamics. Let me check if this is going. Yes, in Langevin dynamics. And then the associated Fokker-Planck equation, that is the deterministic partial differential equation for the solution of, for the probability associated with, generated by a Langevin process. And therefore, we studied that this Fokker-Planck equation has the right physics information to describe the dynamics of thermal relaxation. Why? First of all, because one, it conserves the number of particles, so we don't see anything disappearing during time, which is kind of a very bare minimum request, yet important. Number two, the Gibbs distribution is in fact a solution of the Fokker-Planck equation, which is also quite important. And then we asked the question, what is the physical interpretation of the eigenvalues of the Fokker-Planck equations, provided they're real, because the Fokker-Planck equation is defined in terms of an operator, which I here denote as HFT, P, with H dagger not equal to HFT. So not an Hermitian operator. Since it's not a Hermitian, in principle the eigenvalues are complex. And there's no guarantee that you have any relationship between, say, the left and right eigenvectors, and any orthonormality conditions or anything like this. It turns out, nevertheless, that this is a very, very peculiar form of a non-Hermitian operator, because the same equation can be written as a continuity equation, essentially. So among all the possible forms of non-Hermitian operator, this is kind of a lucky one, so to say. In more mathematical terms, we could find a non-unitary, let's call it rotation in improper terms. It's not a rotation. The rotation is by definition unitary, right? The norm of a vector doesn't change under rotation. Non-unitary rotation that transforms the Fokker-Planck equation into an equation that really resembles a Schrödinger equation, where now H is in fact an Hermitian operator because it has the structure of the conventional quantum mechanical Hamiltonian, with the kinetic energy terms controlled by the diffusion coefficients, and an effective potential term which does not correspond to the potential, but it's controlled by the derivative of the potential. Derivatives, gradients, and Laplacians of the potential. Right? As a result of this fact, the spectrum of this operator is the same as the spectrum of the original Fokker-Planck operator. But now this operator has real eigenvalues because it's Hermitian. As a result, we know that the spectrum of both operators, which is the same spectrum, is made up by real eigenvalues bounded from below. So they're all positive and bounded. Then we perform what we called a spectral decomposition of the Fokker-Planck solution, arriving to an expression, which I will write here in the conditional form as sum over n, all possible eigenstates of the Fokker-Planck equation, which are virtually infinite. Cn e to the negative lambda n t minus t naught, and if you have an initial time, this can be set to 0, doesn't really make a difference. And Rn of x. Well, Cn is equal to the integral of dx ln of x and the initial condition p of x t naught. Right? Rn are the right eigenvalues of the Fokker-Planck equation. So let's write here Rn are solution of H Fokker-Planck Rn equals lambda n Rn, and Ln Fokker-Planck are solution of the adjoint equation. Just a name and a nomenclature. If this is known as the Fokker-Planck operator, this is known as the backward operator, or backward Kolmogorov, and it's nothing but the adjoint of the Fokker-Planck operator. Okay? The spectrum is the same. Not only that, we have seen that Rn is basically e to the negative beta half u of x, phi of n of x, where phi of n of x are the eigenstates of the effective Hermitian operator, the one that looks like quantum mechanics. Right? I'm repeating things we have already seen, just to make sure that we have everything under control. Well, L of n is e to the plus beta half u of x, phi of n of x. So, one major conclusion of last lectures was that the physical interpretation, this equation tells us that the physical interpretation of the eigenfrequencies are the relaxation times, are basically relaxation frequencies or relaxation rates, inverse relaxation times. And that the fact that the lowest eigenvalue is actually 0 is crucial because the zero associated zero solution is in fact the Boltzmann distribution. So since we have, so basically this is telling me that the probability to find the object time t scales like, okay, sorry. Here, this is, to be more precise, this is the probability which depends on the initial condition when the initial condition is being integrated. Right? The expression from the conditional probability, x naught, t naught, is the same equation, but now if you want, my initial condition is the delta function in some initial point. Right? So this will become sum over n e to the negative lambda n t minus t naught, left of n x naught, right of n of x. Right, I'm replacing p x t naught with the delta function in x minus x naught. If I want the conditional probability to be at x naught. Right? So, going back here, the probability becomes Boltzmann, or Gibbs to be more precise, plus corrections that go with lambda 1 t minus t naught are 1 c1 plus other corrections, so that this lowest non-vanishing eigenvalue which is in fact the second lowest eigenvalue overall, is the so-called thermal relaxation frequency, or relaxation rate, the inverse time it takes for the system to attain thermal equilibrium. So if I want to make a simulation that actually samples the Boltzmann distribution, it has to last a time comparable or larger than 1 over lambda 1. Okay? Again, I'm going fast because you can find this in the previous lectures. Over the last lecture, we made a little step forward. We made a little step forward in this discussion and analyzed how does the spectrum of thermal relaxation look like in general. And we discovered that there is a very rich connection between the structure of the energy landscape, in other words, of the function u of x that enters the Fokker-Planck equation, the lowest Born-Oppenheimer surface, if you want, as we interpreted it from lecture 1. Okay? The structure of this determines the presence of gaps, of spectral gaps. In other words, if the energy function contains barriers and basins of different heights in units of h bar, A of kt, let's say kt is smaller like this. So in this case, we have a barrier that is much larger than kt, but we also have multiple barriers that maybe are slightly larger than kt or so on. These properties reflects in special feature of the gap. The larger are the energy barriers, the longer it takes for a stochastic process in one place to bring you across the barrier. It takes a time that scales exponentially with the height of the barrier in units of kt. And this means that basically, in the presence of barriers, thermal relaxation, the attaining ergodicity is delayed exponentially. As a result of which, at least the first eigenvalue of the Fokker-Planck equation becomes exponentially close to 0. We'll see that, in fact, there will be a relationship between the number of basins that we see and the number of eigenvalues that pile up underneath a given threshold. So the spectrum will be, generally speaking, gapped, with gapped, potentially multi-gapped. For instance, as you see here, there are some fast relaxation processes, which nevertheless are slower than just a smooth barrier. This will tell us that there are some very fast relaxation processes associated with thermalization in a smooth barrier, but then there's a slightly slower relaxations which come with overcoming the small barrier, and overall another big gap, and then a very much lower eigenvalues that are associated with an extremely long relaxation time for navigating the entire energy landscape and overcoming extremely large barriers. This is what people say or refer to when they mention the fact that the energy landscape of macromolecules is rugged and complex. Right? And that this multi-scale ruggedness induces an extremely complex kinetics. But most importantly, it generates a rare event problem. Okay? A rare event problem is a problem that naturally arises anytime the simulation time is exponentially long, with decreasing temperature if you want, which means that your system spends, say you have, let's suppose for simplicity we have a one-dimensional energy surface. Suppose we have one-dimensional energy surface. We have time here. Say my energy surface, let's say, has three values. That's negative, 1, 0, and 1, for sake of simplicity, right? So if this is the x-axis, I would say negative 1, 0, and 1. So suppose we start next to here, just slightly south of negative 1. That means that we start here, right? The system will rapidly equilibrate in this valley, start oscillation, and this is called thermal oscillation. It's not a true bona fide oscillation because particles are not really going back and forth according to any harmonic function, but they're called thermal oscillation because the system on average explores this region until every so often the system makes larger excursion towards this point, that is, roughly speaking, minus 0.5, right? About 50% of the time, it arrives to this point called the transition state, and it tosses a coin, basically. If the next fluctuation will be on the right, very likely the particle will roll off towards the next basin. Conversely, if the next fluctuation will be negative, it will likely to go back. So the transition state, you might associate it as the configuration, or possibly the ensemble of configuration if the system is more complex than just a one-dimensional particle. The configuration for which you have 50% probability to returning from your previous basin. Okay? Now, good. So about every 2 times the system reaches the transition state, it makes it to the other side. So here it is. One time it failed, the second time I arrive here. Notice that this transition is extremely fast. So, in fact, what we mentioned is that the time to perform a transition on a productive segment that connects two values is called the transition path time, or TPT in short. This scales doubly logarithmic with the mean first passage time, which is the time you have to wait for crossing the entire barrier. So the waiting time is doubly exponentially long than the crossing time. I'm not aware of any physics relationship that is more compressing than the double logarithm. So let me put it in numbers. So let's take a characteristic time scales. What is a characteristic time scales for macromolecule? For instance, is the time scale it takes for a system to equilibrate in a basin. Of course, it very much depends on the system, but I think it's fair to say that for most systems of interest, this time scale can be, reasonably speaking, in the microsecond time scale. Okay? So, for instance, you have a particle that is say, the local thermalization, you denaturate the protein, you remove the denaturant, you ask, how long does it take before I get to the room temperature denatured state, where it has to locally equilibrate a Gibbs distribution in the denatured state? It's, roughly speaking, is microseconds. Okay? So let's take tau naught to be microseconds. Now, the mean first passage time very much depends on the system. But we discussed last time that it can vary from, say, typically milliseconds onwards. So let's make two extreme cases. Let's take a t mean first passage time to be a millisecond. Let's say, yeah, let's do 1 millisecond. That is 10 to the 3 microseconds. Okay? And let's take a much longer case in which, say, tau mean first passage time is in fact a second. These are not crazy numbers. If you take just out, a small globular protein is typically in between. The prion protein, the structural domain of the prion protein, just because it's a protein I happen to know, has in fact a folding time in the milliseconds. Canine lysozyme has a folding time in a fraction of seconds. So these are not really crazy numbers. So let's say this is 10 to the 6 microseconds. So let's take a look at what the transition path time would be for these two systems. Well, the transition path time would be of the order of 1 microsecond times, let's call this protein A and this protein B. Fast folder, relatively slow folder. There can be proteins that are much slower in folder than the seconds. For instance, we folded the proteins once that folds in hours. But these are a little bit of an extreme case. Okay? So let me call it slow folder even if it's not really extremely slow. Okay? So let's consider the case A. That's going to be 1 milliseconds times log of log, right, of 10 to the 3 microseconds. Now, divided by microseconds, divided by tau naught, right? So let me take away microseconds. This is 1 tau naught microseconds times log 10 to the 3, which is log of 3 log 10. Right? Which is, I hope I don't make stupid mistakes, but this should be log 3 plus log 10. Right? Okay, once again, 10 equal 9 as far as I'm concerned. After just very, very rough estimates, the logarithm is not a fast varying function. 9 is 3 to the half, so that's 3 half. That's 2 log 3. Right? Now, log 3 and log 2, log 3 is log 2 plus log 3. And you see these are all numbers of order 1. Right? So, in other words, in the case in which this is a fast folding protein with an order of magnitude 3, this is just barely larger than tau naught. Okay? Maybe 2 tau naughts. Okay? Okay, that's done. So let's do case B. Now, this time is still tau naught, but instead of having log 10 to the 3, we have log 10 to the 6. But you immediately realize that this doesn't change things in a very, very dramatic way. Because this is going to be log 6 log 10 So the only thing that changes is that instead of having a log 3 here, I get a log 6. And everything else goes down the same, right? Now, log 6 is not that far from log 3. Say, assume even if 6 becomes 9, this is just twice as log 3. Right? So that means that basically what you're doing is just adding maybe factor 1.3, 1.5 to tau naught. So the point is that the tau mean first passage time is always within a few microseconds, regardless of how slow is the folding process, or stated differently, how rare are folding events. Now I'm using protein folding as a paradigmatic example of a thermally activated process, but of course it generalizes to any thermally activated reaction. So basically what it's telling me is that I can wait forever here, but basically when I go. And the time it takes me to do the transition here is always extraordinarily faster than the wait time. Now, if what your interest is to study is how conformational transition occurs, which is a very common problem to be tackled, because one question you might be asking is, where do I end up being, right? And for that, you really have to explore the entire energy landscape, right? Another important question is, how do I get there? And for that, you have to be very, very carefully measuring this. Right? This arises two fundamental problems. The first problem, actually three fundamental problems, which we have discussed several times, but it's time to go into actions, so to say. The first problem is, how do I explore, how do I sample the Boltzmann distribution very efficiently? Okay? That's one side of the rare event problem. How do I sample the Boltzmann distribution in a way that is more efficient than just integrating forward equations of motion? The other question is, how do I sample transition paths very efficiently without having to explore, to spend an exponentially long time to observe something that I don't see and I'm not interested in? And over the last lecture, we went quickly through methods that are specifically designed for this problem, the exploration problem, and for the path sampling problem. Right? And we did not discuss many enhanced sampling schemes. We'll do it possibly at the end when we do some AI. But at the moment, I just want to pick it there. Okay? But there's also a third problem, which is, how do I make sense of this? I want to just give you a feeling how horribly hard is this problem. Say, you might want to say, okay, I want to learn how molecular processes occur. I'm going to sit down and watch a long MD trajectory. I have visual visualization codes like, I don't know, BMD, right? Chimera, whatever you want. You sit down in front of a television and you watch the molecules wiggling around until you see something that catches your eyes as potentially interesting. For this stage, you might see the protein all of a sudden folds. Okay, let's see. Well, let's say I save a frame every 100 picoseconds, which is a typical figure, right? Your long trajectory saves delta t 100 picoseconds. Okay, suppose you have a 1 second long trajectory, right? So t is 10 to the 7 delta t, right? Because it's 10 to the 6 microsecond, and 1 microsecond is 10 times 100 picoseconds. Right? Okay, so now let's say I watch a frame. I don't know, I want to see 20 frames per second. That's pretty fast, because every second I see a lot of going on. But let's say 10 for doing calculation, 10 frames per second, because I really want to understand something. It's not easy to see 10 frames per second if you really want to understand something. But let's say, I want to say 10 frames per second. Okay, that means that I have to watch 10 to the 7 frames, and one of which is 1/10 of a second. Time watching is 10 to the 6 seconds. Only watch a single trajectory will take me, well, you know that an hour is 3,600 seconds. We are talking about 1,000 hours. Divide 1,000 by 24, right? Divide 1,000 by 10 is 150 days of non-stop watching. If you survive that, certainly your concentration will not. Okay, clearly, this is an interesting example that tells you this is not a problem for human approach in the conventional sense. We need to use math. We need to be smart. Just looking at things as an experimentalist would do an experiment, right? It's not going to work. It's not a virtual microscope in some sense, because the virtual microscope, you can sit down. First of all, it's not a virtual microscope because it's a simulation and it's not an experiment, which is a fundamental, crucial, gigantic, huge difference. We are simulating things. We are not seeing things. Galileo puts turn in his grave if we mix the things. That's why I hate the expression numerical experiment. I sort of think is kind of a curse. Either you do numerics, in which case you do theory, or you do experiment, in which case you do measurements, real measurements. But that's my personal crusade, if you want. But what I'm trying to say is, clearly, in a microscope, I sit down and watch. Here, even watching is not an option. Okay? So, the purpose of the next move is, how can we make sense of trajectories? They're extremely long. And we want to learn something out of it. And today, we're going to go into the field. So we're going to do the idea of coarse-graining, configuration space, and kinetics, inspired by the principle less is more. Picture yourself. You are an alien that is dropped in Times Square. For some reason, in some Avenger movie, there is an alien that all of a sudden finds this. He has no idea how humanity works, but he really understands that there are people walking, moving at a certain speed, on feet, and other strange objects that we call cars that move on streets. He has no idea about that. But after a while, he realizes that people moving on wheels are typically cabs, taxis, so they're yellow. Let's simplify that all cars are yellow for simplicity. So you probably don't remember, you don't know how Times Square is done, but Times Square in New York has kind of an island where people can walk, and lanes here and there. Right. So we, as humans, know that that's where the cars go, right? But there are people crossing all the time because, you know, there are a lot of tourists in Times Square. So if you take a snapshot in every single moment, you will probably see cab, a guy walking, another guy walking here, another guy walking here, with a cab passing, right? A lot of people here, sure, in the island, because, you know, here they sell tickets for Broadway and stuff like that, and people take pictures and blah, blah, blah. And there are people here and here. But it's a complicated picture. Now let's take an opposite standpoint in which what the aliens will do will take very long exposure photographs. So effectively, this will lower the time resolution and produce bands. You will get yellow bands here, because many cars have passed. All of a sudden, the structure of the square becomes clear. That's where the cars are. That's where the cars are. Instead, if you want to get the same information microscopically, you first have to observe a lot and then average out. Because the detailed information is not always more instructive than the low detail information. So there are situations in which less is more. Okay? Macromolecular simulations is one of that. Sometimes we want to coarse-grain the information to a level that makes it understandable. Now, today we're going to talk about one way of coarse-graining the information, which is at the same time also an enhanced sampling technique, as I will discuss in a moment. So to say, an approach that takes two birds with one stone, enhances potentially the sampling and lowers the cost and enhances the interpretations of the results. And these are called Markov State Models. Markov State Models. I don't want to write them out. Now, there are many ways to introduce Markov State Models. But the matter of fact that the real mathematical framework that established Markov State Models as a rigorous constraining strategy was only developed relatively late in the early 2000s. People have used heuristic argument to describe complicated systems with discrete jumps. But the formalism underneath the possibility of doing this in a rigorous way and how the parameters scale has only been cleared out when I was already in PhD school. It's kind of interesting. So, what is a Markov state? Well, let's first give a heuristic, say, man on the street definition of Markov states. You have a complicated energy landscape. You identify that there are stable basins. So here there are 1, 2, 3, 4 stable basins, right? You give up the intention to follow the dynamics within each basin. You declare that you are not interested in understanding what happens within each of the basins, whether I oscillate from here to here and back, or because this is going to be averaged out anyway at long times. So all you care is what is the probability to be in any of these states at any given time, right? So in other words, you introduce a probability P, or I call it N for being coherent with the nodes, of being in the ith state at time t. You can interpret this as a density or as a probability. A density, if you imagine to put many, many copies of the same system in the same energy landscape and letting the system evolve and see how many of these copies of the system are in any of the states. And of course, in the Largent limit, this describes the frequentistic definition of probability. So you can interpret n as the probability of a single system to be in any state at a given time. Right? Now, the idea is that you want to understand how any of these probabilities evolve with time. Because that's basically what you need, right? You know the initial probability, you know to evolve in time these probabilities. And basically, you can know the probability of being in any of the states at any future time, right? And it turns out that this is simply written as a set of transitions probability. So, in other words, the probability to be in time t is given the probability probability to be in state I at time t plus delta t is given the probability to be in state j, which could be I, and time t, plus the probability of making a transition from state j to state I in a time interval delta t. Now, you will forgive me if I use a notation that is a physicist's notation rather than a mathematician's notation. Because normally mathematicians, when they talk about Tij, they actually mean Ti to j. Okay? When you talk with physicists, since this is a transition probability, it looks like a propagator, right? The propagator, the initial condition still sits on the right, and the final condition sits on the left bracket. For physicists, this is Tij normally means Tj to I. And I'm a physicist, so I'll stick to the second. Okay? Just be aware that if you open a book on stochastic processes, you might need to check whether which of these definitions is being used. Okay? Okay, this matrix here is not any matrix. First of all, it's not symmetric. It's a real matrix of transition probability, but it's not symmetric because the probability from going from here to here involves overcoming this barrier. But the probability of going from here to here involves overcoming this barrier, which is roughly speaking almost twice as large. Okay? So Tij is not equal to Tji, and we are again back to the problem that we have a matrix that we don't know whether it contains eigenvalues that are real and blah, blah, blah. But again, this is not any matrix because we know that the system is going to go somewhere, right? And in fact, this matrix obeys sort of a continuity equation, which in this case is the sum over all endpoints of my transition is going to be 1, right? So, if you want the rows of this matrix add up to 1 for every column. Right? This is called a row stochastic or net stochastic matrix. And again, if you have a row stochastic matrix, then you're a little bit like in the situation of the Fokker-Planck equation. And in fact, it's not coincidence, as we shall see, that we are in similar situation. We have a non-orthogonal matrix that behaves nicely compared to average no orthogonal matrices. Because if you have a row stochastic, then what did you discover? That the spectrum is real. Then the lowest eigenvalue is actually 1, and the other ones are less than 1. So lambda 1, lambda naught is greater than lambda 1, greater than lambda 2. In other words, while for the original Fokker-Planck equation the spectrum was bounded from below up, they are all real but bounded for 1 down, and we will rewrite this in a form which will reverse and get something from below up, as we'll see in a moment. Okay. Anyway, and because of this, there would be a distribution such as T, J, I, and not I. Sum over J is equal to and not I. Sorry. J, not sum over I, and not J. So there will be a stationary distribution, a distribution that won't change. So in other words, the equilibrium distribution. So just as in the Fokker-Planck equation, in the Fokker-Planck equation, the fact that this was a matrix that was basically expressing the continuity equation. This was generating very specific results. For transition matrices, the row stochastic condition, which expresses the conservation of probability, again, generates basically the same constraints. You have an equilibrium distribution, you have a real spectrum therefore with spectral relaxation interpretation. Okay?
So I didn't really understand the equilibrium distribution.
Yeah. This tells me that if I start from a naught at time t, after a time delta t, the new distribution is again a naught. You see, the new distribution is the distribution at the previous time step times the transition probabilities in the time step. But if my previous time step is this particular solution, the eigenstates, 0 eigenvalue of t, I, j, then after a time d, delta t, this distribution won't change. Which means that I have obtained a stationary distribution. And we identify the stationary distribution, of course, with the equilibrium distribution. Okay? So what have we learned? We have learned that if I for a moment heuristically, then we will need to make probably a better mapping between the microscopic dynamics and this coarse-grained heuristic representation for now. Well, this is basically a representation in which my original problem is turned into a network in which each node is one of the states. So remember I had 5 basins here. Now I have erased them. So there are 5 states. 1, 2, 3, 4, 5. In principle, each can transition to any of the others, but a direct transition from the leftmost to the rightmost in that case was not possible, right? So you in principle can have some finite connectivity, but this is a directional network, meaning that the links in the networks have an arrow. Right? And the edges in the network, the directional edges, are given by the transition matrix. And this network has a stationary state. which you can identify as the ground state. Sorry, as the Boltzmann distribution probability. Okay? And by the way, given this mapping from stochastic processes to Markov processes to networks, you can now use graph theories, anything we know about theory of networks, and apply to this particular kind of networks. Yes?
But the equilibrium state should be an order with only incoming edges.
No. The edges are not, the edges are transition matrices. I to J, so this is, okay, let me put it this way. An edge from J to I is the probability of making a transition in a time delta t from state J to state I. This is nothing to do with the equilibrium distribution, because it's the ingredient that sits there. The equilibrium, the distribution is n that multiplies that. Okay? So the edges will be the same throughout the entire time. What will change is the numbers associated with each node, let's call it n, I, which represent the probability for a system to be in any of the nodes at time t. So if you want, the network is wired up with fixed edges, which parameterize the underlying dynamics, and the dynamics of the networks is given by the population of the nodes. Right? Okay. Once again, remember the beginning of this course when we're insisting on the idea of rigorous effective theories based on renormalization group. What is the rigorous effective theory based on renormalization group? It's a theory which gives up that, if you want, that capitalizes on the principle that the details of short time or short distance physics are irrelevant for understanding the long time dynamics. And if this was possible, then you would replace all of these short distance physics into a fixed number of effective constants. Our analogy is always the same, the multiple expansion. The details of a short distance structure of the source charge distribution can be replaced by a fixed number of constants that are the charge, the dipoles, the quadrupole moments, depending how complex our field actually happens to be, right? Now, here we are under a very similar circumstance, because there's an underlying microscopic dynamics that depends on the force fields and has a very short integration time step, small dt, which is of the order of the femtoseconds, if you remember. But this dynamics is the microscopic dynamics, will only tell us about, will also tell us about wiggling and thermal oscillations within each of the states, which we declare these are short time dynamics we are not interested in following. So all we want is the time to have a resolution delta t that is sufficiently long for the system to have time to have thermalized within each well, so that it makes sense to speak about the probability of to be end of the well. So it has to be longer than the thermalization within each basin, yet shorter than the typical transition time between the wells. This is called the lag time. And how long is the lag time? Well, it very much depends to what degree I want to be, to what degree am I ready to wash out short distance dynamics. For example, are you following me? For example, like I told before, I might be in a situation which have multiple structures. I might be willing to say, okay, I'm only after big processes. So perhaps I make this a little bit more explicit by extremizing this a little bit. Nature is always complicated. It will always put you into in-between situations. But let's suppose there is no such a thing for this. Well, I want to have something that neglects the very, very short dynamics here, but takes into account of this dynamics. So I will have to assign a state to each of these small well. 1, 2, 3, 4, 5, 6, 7, 8, 10. Right? In that case, my delta t has to be smaller than the typical waiting time between these two nearly separated wells. So, relatively short. Okay? Conversely, I might want to take even a coarser grain approach and say, hey, I'm only interested in dynamics between large and very slow dynamics. So I don't really care about these dynamics. It's all within this macro well and this macro. But then all of a sudden I have 1, 2, okay, here is somewhere in between. Let's say these are small barriers, 3 states. But now my delta t has to be lower than the typical time to overcome this very large barrier. So I get a smaller network, but with much lower transition probabilities. Because now the probability to go, well, I have to choose t large enough for this probability to become, if I were using the same delta t, the probability would be very small. Now I use a much longer delta t because the probability to go from here to here in a longer delta t. Right? So now suppose you have the very long trajectory that we were mentioning before. Right? We have this multi-seconds MD simulation. Nobody has ever produced a multi-second MD simulation. This is just in the ideal case in which we could actually generate a multi-second MD simulation. People have been generating milliseconds, which is already hours to watch with our criteria, if you remember. But anyway, suppose we have a multi-second MD simulation. One thing, and we know that this simulation visits many of these states, if not all, in time in a given sequence. Right? Now we might invent a criterion to assign for each time the instantaneous configuration x of t to any of the state aside. For instance, in our example, if at the each time after I'm here, this is state number 1, the simplest criterion is I will be the shortest distance from the minimum of the basin, for instance, right? Now this guy is closer to this point than it is to this point, I associate it with that. That has a problem as an association mechanism, as we shall see. We will need better definition of proximity. Better ways to associate a configuration to a state than simple geometric proximity. But let me first say, suppose we don't have a problem in associating states to configuration to states. Now clearly a trajectory that does this, then does this, then comes back and does 2, and then finally gets here, contributes to the probability from start from here to end up here in a given time. But in this simplified description is 1, 2, 1, 2, 3, 2, 3, 4. You see? It was in state 1, it was 2, 1, 2, 3, 2, 3, 4. Now, all of a sudden, I can look at the network and say, okay, say state 4 was the native state, state 1 was the denatured state, and these are a bunch of intermediate states. And all of a sudden, my trajectory is, I started from here, I went to this intermediate, I came back, I went again to the intermediate, I moved to this other intermediate, went back, moved that, and reached the native state. And since many trajectories end up visiting the same intermediate states, now if all trajectories visit different intermediate states, then clearly this compression doesn't bring much edge because every single trajectory remains different from any other single trajectory, right? Vice versa. If multiple microscopic trajectories visit the same macro state or Markov state, then clearly this leads a very efficient compression. Because I don't need to distinguish what exactly two trajectories do to get to that state, as long as they go from the same initial state to the same state. So just as much as I am not really interested in understanding what the specific taxi is doing in Central Park, as long as I know that the taxis are here and here, and they move this way and this way, right? In the protein folding simulation, I may not be interested in taking two trajectories that will always be different in the microscopic space. But they might visit in the same order, the same states. So to within this resolution, they describe the same process. Less gives me more information. It allows me, and now let me go back to an example that I was telling at the very beginning of the course. Remember when I said I throw my chalks in the room, and the chalks eventually ends up in the corridor. But every time I send the chalks, it will make a different trajectory. So how do I learn about how the chalks gets to the corridor? If any experiment I do will give me different results. Well, the intuitive answer was there are two doors here. One is on the left for the viewer, not for me, it's my own right. And one is on the right for the viewer. And if you were to do a Markov state representation, you will discover that there are basically two states you can go to, the left door and the right door. And all of a sudden, a virtually infinitely complex process becomes extremely simple. The chalk gets out by going either to the left door or onto the right door, period. Okay? So this is how you start to make sense to complex information in a complex energy landscape by lowering the resolution of configuration space and kinetics. And if you lower structural information, you simultaneously lower temporal information through the lag time. The two are connected because you can only visit as much configuration in a given time. Okay? So, Markov states are interesting ways of analyzing the system, but how do I go from my microscopic trajectory to a Markov state? Well, it turns out it's a long process. First of all, so the question is, are you with me so far? How to build a Markov state model? Because we probably agree at this point that it's a good thing to be doing. But how do we do it? Now, let me start from the assumption that we are under the simplest scenario in which we can do ergodic molecular dynamics. That we don't have an exploration problem. Okay? So we have virtually infinite computer power. Our problem is only that of interpreting the results. Okay? And then once we are clear with that, we go to the next step and we'll say, okay, now what if I have a limiting problem in my computer resources? Okay? But let's stick to the fact that we have infinite computer power. Now, the first thing we want to do is to identify each x of t with a sequence I, j, k, say I1, I2, I3. Well, these are all indices that label which states are you visited after a time. Delta t, delta t, delta t. This is the large delta t, lag time. For instance, this could be 1, 1, 1, 2. Means that for the first 3 macro time intervals, I remain in state 1, and then I jump to state 2. Okay? This is not the order of which you visit the states. This is where you are after a given fixed time interval. Okay? Brilliant. So, first of all, you want to featureize your trajectories, but you don't know what 1, 1, 2, 2, 2, 3 is, right? So this is already one step ahead of what you can actually do. First, you have to discover the states, because nobody tells you what the states are, right? I'm in saying that you can do this, I'm assuming you know what state 1 is, state 2, state, but all you have is a bunch of configurations. So first of all, you want to see if the configurations in some feature space, let me just finish the sentence and I'll tell you what the feature space is. Configuration have like a clusterized decomposition. So anytime I see that, what is a feature space is a set of collective variables that are sufficiently informative for me to assume that I don't need to resolve any further information. Let me give an example. I could featureize a molecular simulations of a polyalanine peptide by the dihedral angles of the polyalanine, right? Because alanine has only H as a side chain, so it doesn't have any structural information on the side chain. So the only structural information is the dihedral angles. One of the dihedral angles is always essentially locked, so there are basically 2 dihedral angles per protein, per peptide bond. So if you have n amino acids, you have 2n features. You have 3n coordinates, so many more, but only 2n relevant dihedral angles, right? Now, if I plot, so that means that my trajectory is a point in a 2n dimensional space. If I build a metric in this 2-dimensional space, 2n dimensional space, and I see this is the distance in the 2-dimensional space, in 2n dimensional space, and I see that the distance, or somehow in this featureization, the system remains in the same configuration for a long time, and then goes to a different place in this multi-dimensional space. Right? I can identify each of these with a different Markov state. Okay? Again, I'm assuming that this is a trivial problem. It is not. A lot of literature has been gone into doing this in the proper way. And to my knowledge, the best concept to digest about how to do this efficiently is the concept of kinetic distance, which I will elaborate on later. But for now, we assume that you can easily understand, maybe structural proximity in some feature space is good enough, okay? Fine. Then, okay, I see the system that remains close to this particular set of features. Phi 1 equals phi 1 bar, phi 2 equals phi 2 bar. This is the variable, and this is the average value that I see here with small variation. And maybe here, phi 1 is equal to phi 1 bar prime. And maybe phi 2 is equal to phi 2 bar. This feature is the same, but this is different, right? For instance, one dihedral angle remains the same, but the other has flipped. So this is a new configuration space, configurational state. Okay? Sure? So I scan through my trajectories. I have a criterion to say that this has been a slow, fast decoupling. It has to stay in the same state for sufficiently long before it goes to another. Okay? And all of a sudden I have collected n different of such states. Now see, I have these states to label. So first step is identify the Markov state through clustering configurations into by featurizing molecular dynamic trajectories and look at clustering in some metric. Okay? After I've done that, I'm done with this part of the job. I've constructed nodes. Now I have the nodes. There are 5 nodes. But I still haven't built a model because what I need is also the edges. Okay? Now, the way you do it, you apply the definition of edge is the transition probability to be in the node I at time naught and end up in node j at time naught q plus delta t, right? So basically now, you look through you have an automatic version, a code that scans through your trajectory, sees anytime you end up in state I, right? It jumps delta t times ahead and see how many times you end up in state j. Sometimes you will be still in state I, and other times will be in state j, right? And so by counting out the number of relevant events, of transition events or residence events, meaning you might even stay in the same place after time delta t, you can estimate Tij delta t from MD. But this is a stochastic inference. You have to use, if you want, central limit theorem. On average, my transition time is given by transition probability is estimated from a number of finite events, right? But in principle, you can do this, and if you have a sufficiently long trajectory, this will prove right. But there's a problem. As you're starting to realize, there is always the next problem. What is the problem? Is that this matrix Tij must be rho stochastic, right? It means in this rho stochasticity implies a very strict sum rule. The sum of all the rows given a column has to add up to 1, right? Now, if each of these elements has been estimated stochastically, right, the probability to end up exactly to 1 is 0. Because there are uncertainties, right? Which means that your matrix, the naive definition of matrix, will not be exactly rho stochastic, right? So you need to be a little bit more accurate and more careful in dealing with this problem. So what people normally do, they use Bayesian methods to infer the most probable rho stochastic matrix given a set of measurements that they see. So this is actually by Bayesian inference. rather than by direct counting, because the direct counting will give you a matrix that doesn't even have a stationary state and a real spectrum, because it's not row stochastic. So what you really need to do is to find the most likely row stochastic matrix compatible with the observation you're doing. Now, nowadays there are tools that do it for you in Python. You don't have to do it yourself. And once AI is becoming a commodity, even if you had to do it yourself, you probably would just ask one of these AIs to generate a code that does it. But nevertheless, you see this, right? So now in principle, I have done everything I needed to. I started off with the molecular dynamics, and I have achieved the Markov State model representation of the dynamics. I know I can get the equilibrium distribution right away by diagonalizing the matrix and getting the ground state, the stationary distribution. But I can also get all the dynamics I want. Right? So in principle, yeah, I can get the dynamics. How do I get the dynamics? I told you I can get the dynamics. I have a Markov State model. How do I measure it? Well, I need a way to integrate the Markov State model, right? And there are many ways to do that. One way is to start from a state, I, which you choose according to some initial probability, and then have a Monte Carlo method propose a new state where to go. This will become basically generating a stochastic discrete trajectory, right? This is called kinetic Monte Carlo. Or you can try to get directly the solution of that equation by diagonalizing the operator. So what do I mean by that? And this is the last topic of this lecture, don't worry. It's been a long. So how do I, so once again, let's wrap up what we have done. We have done a lot of motivation discussions. We arrived to the concept that Markov states are relevant. We discussed how you actually build a Markov state. And now we are discussing how to solve a Markov state model. Okay? So let me write it. If I can find my eraser. No? Erasers is gone. Oh yeah, it's in here. So now I erase all this. So now the question that I'd like to address is how to solve for solve a Markov state model. Right? So now we assume we have our Markov matrix. We have our master equation. This is called the master equation over there. This is the master equation. And now we want to find what the probabilities as a function of time, which means given ni at t equal naught, we want to find ni at t greater than t naught. For instance, the initial configuration might be, we know the system is in that very Markov state, in which case ni equals t naught is 1 for one state and 0 for others. It's a vector, right? Of positive numbers between 0 and 1. Right? And after sometimes the probability distributes according to some law that we want to figure out. Right? And for instance, we might discover that most of the time your chalk goes through that door because I'm throwing the chalk in this direction typically, and the angles are such that the probability as a function of time would be nothing is on the corridor for some times, and after some time, the probability of being just behind that door will grow up a little bit faster. Which means that this very vector n1 or n left for you has a faster growth than n right. Okay? And this will tell me that most likely, if I'm interested in the process, immediately the system goes through that door. You can turn that into macromolecules and say most of the time you form that contact first. You see how you start to build qualitative information. But we need to be able to solve for this, right? I will provide two ways. The simplest one is the, conceptually simple, is the kinetic Monte Carlo. So, the kinetic Monte Carlo works as follows. You have your states. You have your network of states. They are directional state networks as usual. Say you start at some time from this state. You pick up one state according to the initial probability. Say the initial probability is flat, you pick any of these states. The initial probability is extremely narrowed, you pick the one where it is narrowed to. Okay? Now, this state is connected to certain states, not to all. In principle, it's connected to all, but you can neglect some connections. It's the same thing, right? So, for instance, this state 1 is connected to state 2 and state 3, but not to state 4. But the arrow in the direction from state 1 to state 2 are thicker here, representing a larger transition probability, than here, representing a smaller probability. Right? So if I take the probability from state 1 to state 2 and divide by the probability of going from any place, you can go to 2 or to 3, right? This number is between 0 and 1. T13, defined in the same way, is another number between 0 and 1, right? And the sum of the two, guess what, is 1. Right? So I can take an interval between 0 and 1 and break it into two subparts, one proportional to this ratio, let's call it ratio 1:2, and this is ratio 1:3. But this is proportional to our 1:2, and this is ratio 1:3. Between 0 and 1. Now I sample a random number between 0 and 1. If it happens to be here, I go to state 2. If it happens to be in this range, I go to state 3. Right? And so from 1, I go, say, to state 2. Now I look at the states where state 2 is connected to. Now there are 3 states. 1, just state 3, 1, and 4. Okay? Now I have to evaluate 3 ratios, not 2. I have to split my 0, 1 interval in 3 parts and sample a random number. And this will take me possibly to another state or possibly back to state 1. Depends what a random number between 0 and 1 will be. Okay? So by doing this, this is a Markov process because at each time, I don't care what happened up till now. Every time, new game, toss a coin, decide. Clearly Markovian process. Now, this way I generate trajectories that are constrained into this discrete jump state. Okay? Discrete jumps between microstates. And then, at every single interval, I construct the probability from frequencistic definition. Okay? So kinetic Monte Carlo is very simple to implement. It's basically an undergraduate exercise. The second approach, I call it projection or diagonalization. You'll see in a moment what I mean. Well, n t plus delta t I is equal t and t. Let me write it as a vector now. Just n's are the number are vectors, integer vector, no, not integers, sorry, discrete vectors with long as many as nodes in the network, and they're all bounded between 0 and 1. Okay, so let me compute n of t plus delta t, negative n of t. Just let me look at the relative change in the population. Okay? This will be t negative 1 n. Now I divide by delta t. Okay? This is nothing but the time derivative of the vector in the appropriate limit of delta. But now you see, I want to do one more step here. One is, of course, the identity matrix there, not just the unity. Right, it's an n by n matrix. Now you see, the next point is observing that t becomes identity in the limit of short delta t. In other words, if I wait too little, I don't go nowhere, right? The probability to make it to another state in a time that is much smaller than a typical transition time will be 0, right? So I will be becoming diagonal, right? So for small delta t, this is 1 plus something proportional to delta t to the matrix K negative 1 divided by delta t. This is the Taylor expansion of t in small delta t units times n, which is basically k times n. So I've got to the equations n equal n dot is kn. This is an equivalent formulation of the master equation, formulated in terms of derivatives of n, not discrete changes in time. K is called the rate matrix. And it's basically the same information of t expressed in terms of rates, and is defined by this, by the way. So this is the way you are. If you know t, you get k by this equation. But the physical interpretation is how many times per unit time you go from one state to the next. Okay, so in other words, let's take two states, just to make things clear. Let's call it number, the change in states in the number in the state left is given by k, say, so in general I have to state n is equal to n left and n right. K is a square matrix, right? K is a square matrix, which I will populate in a moment. Now let's see physically how to infer the properties of this matrix, which are basically direct consequence of the row stochasticity we discussed before. Let's break this into components. So I have n left and n right. Okay? The change in population of n left is given by the population in n right times the probability to go from right to left. Right? So this tells you that if I had some system in the right state and with a given rate it fluxes to the left state, it will increase the population of the left state. But at the same time, there will be systems that at the previous time were in the left states and leave. Right? So this will be k left to right and left. What about the population? So if I write it this way, I have a negative k right left, positive k, no, sorry, right left, yes, left right, okay? And now, what about the population in the right? Well, the population in the right is given by the number of states in the left times those who made the transition from left to right. Negative, the number of population in the right and those that left right to go to left. So I got k r left, negative k left right. So you see, in this formulation, columns add up to 0. Before, in the discrete jump formulation, columns add up to 1. But now we're talking about rate of transitions. And because of that definition here, okay, which I just erased, but you got t minus 1 divided by delta t is equal to k. Because of this definition, the fact that these add up to 1 on the column implies that the column add up to 0 in the k formulation. You see? Okay, so basically we know how to build either a discrete or a continuous jump. In the continuous formulation, I have time derivatives. In the discrete formulations, I have discrete jumps. Now, the beauty of the continuous formulation is that I can use the properties of first order differential equation. Because you see, in the continuous formulation, my master equation is now n dot kn, right? which again looks a little bit like I psi d by dt equals h psi, right? Schrödinger equation with the difference that I don't have an I here, but it's still some first order equation with some operator on the right? So this means that I can build a time evolution operator and say that n at time t is given by e to the k t n of time 0. Right? Okay, let me adopt the Dirac notation so that the next step is very familiar to you. I will do n of t, right, equals e to the k t n of 0. I've just added a Dirac notation. Right? Now what I can do, I bracket this, sorry, not here. Here I do the same trick as I use always. I put 1, and 1 is the sum over projecting over, I use k, the k eigenstates of, well, not really. I have to distinguish left and right eigenstates, as usual. So this is going to be left and this is going to be right. But basically the point that I want to make is that if I can diagonalize this, and I have the eigenvectors, in principle I can evolve these to any future time. Just you would do quantum mechanics. Now, this is clear and simple if you have two states. If you have 10,000 states, diagonalizing a 10,000 matrix can be a little bit complex, right? So rather than doing direct diagonalization, what you can do is a much simpler approach. And you say this is equal to e to the k delta t to the n, and not where delta t times n is equal to t. I'm splitting t into n delta t steps. You see this equation? This is n delta t. T is equal to n delta t. Right? Now I can bring this n up. Right? And up. N was here, I bring it up. So now I have basically that I have n times a small time evolution of time delta t. So basically what do? I start from my initial distribution and I apply this object n times. Anytime I apply this object to this initial state distribution, I get the population after a time delta t. See it? This is my propagator for time delta t. So if I apply it to my initial state, I will get the population after time delta t. I apply it twice, I get it after time 2 delta t. I apply it n times, I get it after n times delta t, which is after any arbitrary time. So basically, by performing matrix vector multiplications, I evolve the populations in time. So it's time to wrap up. What we discovered, well, not discovered, but what we discussed today is that not only you can build a Markov State model, but you can solve a Markov State model either by kinetic Monte Carlo, or if you feel very strong by diagonalizing the rate matrix or a transition matrix directly, but Most likely, the way you're going to do it is you're going to build a small term. By the way, this is the transition matrix T. And you basically are applying a matrix to the initial state n times to change the population a little bit at a time. So this, if you want, is the analog of evolving a configuration in molecular dynamics, step by step, but you don't do it on the position states, you do it on the populations of the Markov states. Now, since you are dealing with population of Markov states, this delta T is in fact much larger, so you need much fewer steps than you would do in molecular dynamics. Okay? Okay, so I want, since we are 10 minutes past it, but I would add 2 more minutes, you forgive me, because rather than starting from this next time, so I can start a new argument, new topic next time. At the beginning of this lecture, I told you that Markov State models are a way to understand microscopic dynamics by the less is more principle. But I also mentioned that it can at the same time be a way to enhance the sampling. And I'm going to tell you how these Markov State models have been used for enhanced sampling. And the idea is by, I would call it with the name of the first venture that actually Endeavor then did realize this, but you can generalize to any problem. The folding at home. Approach. Now, you may be more technical and say massive parallelization scheme, but I think it pays justice to Vijay Panda and co-workers who made this incredible endeavor back 15 years ago to call it by the name of the endeavor. So at the time people were interested in protein folding, I told you the Anton supercomputer was not built yet, so nobody could really even know if proteins could be folded. So the brilliant idea that Panda and co-workers carried on is there is gigantic numbers of unused CPUs in the world. Take about all the administrative computers that go on idle from 5 p.m. to 9 p.m. All these CPUs is wasted. So why don't we have users all over the world? We exploit global economy, global societies, globalization, so that anybody can volunteer his own computing resources by signing up to folding it. If you do, then you will download a package. And what does this download package? It will take an initial condition from the system, excellent, and maybe crunch 100 nanoseconds on molecular dynamics. I don't know, maybe a little more. Okay? Now, what happens? You can do that in a massively parallelized scheme. So you start from here, and at the beginning you pay a price because at the beginning you start all from the same configurations, for instance. And after a while, some will discover that in that out of millions, some will go to a new state, next prime. Right? Now, the next day, when you distribute your 100 microcycles, you'll distribute it evenly. Right? So now, maybe this guy will discover a new state as 3. The next day, you distribute your millions in 3 ways, and you see that geometrically, you're starting to populate configuration space in a more and more efficient way, of course. So this already will give you a fast way to discover states faster than just going forward in one single direction, hoping that you will visit all of this in sequence. Okay? Because there are so many millions of CPU, you can simultaneously exploit at the same time. So this will give you discovered states. And then, of course, you have to compute the transition. So when you give up this, then you see in your trajectories, You count how many times you went to state 3 coming from state 1 in those 100 nanoseconds, and how many times you went from state 1 to state 5. So as you distribute this, and you also simultaneously on the fly estimate the transition metrics. So while the total amount of simulation is not reduced in the sense that you still have to do a lot. If you sum all of these molecular dynamics, you still do a lot of MD simulation. They're done in a massively parallel ways with very little broadcasting time. Broadcasting is when you stop and say, okay, now I share information between all the computing nodes. Basically every day you can think about it. So you see, it's a very brilliant way to exploiting globalization to enhance sampling. So folding at home was actually able to produce folding trajectories for very small proteins this way back in the days without using any. You can even do it yourself. And I guess now Vijay has gone from academia to VC, venture capital. I think he runs a VC fund, if I'm correct, or at least he used to a few years ago. But I know Greg Bookman, if I remember well, is now leading forward this initiative. You can download and use your computer if you want to do that. You do all sorts of things. Go folding at home and browse it, you'll discover. But you see how much statistical physics and theory-stochastic processes take you far at this point in solving all of the problems that we listed before. Okay? I decided that for now we'll not go, so one thing we didn't do is to do this, connect this heuristic approach to Markov state directly to the focal Planck. And see that if you start from the focal Planck, under certain limit, you recover the correct Markov state model. I will probably say something about this next time, or probably not. I have to decide whether I want to go into another direction. We'll see. But the important thing is, this is the heart of the problem and the heart of the approach. Okay? Thank you.